Hello, welcome to my FOC class. The lecture today will be on Chapter 3. The ARM instruction set. As we have learned from Chapter 2 that the instruction set is the command used to instruct the microprocessor to do a specific task. For example, moving data from memory to internal CPU register, or adding numbers in the registers. In this chapter we will learn some of the important instruction for ARM microprocessor. These are what we will learn in this chapter. The first one is the ARM development flow in terms of program development. Next, we will look at how the data is represented in the microprocessor. Then, we will learn some of the common instruction set in detail. And, the last one is how to write the program for the microprocessor, both in assembly and C languages. This is the ARM development flow where the program can be written in high-level programming language, such as C or assembly language. After the compilation, both languages produce a new file, called object file. An object file is a file containing object code, which is relocatable format machine code that is usually not directly executable. A linker is a program that takes one or more object files generated by a compiler or an assembler and combines them into a single executable image file. And finally, to the binary or bin file. In computer, integers are often represented in 8-bit byte, 16-bit halfword, and 32-bit word quantities. The byte-size data is represented like this. This is called bit 0, bit 1, bit 2, bit 3, bit 4, bit 5, bit 6, and bit 7. Meanwhile, for the halfword data, this is the bit 0 and here is the last bit, which is 15. As for 32-bit data of word size, the last bit will be the bit 31. The unsigned representations make the assumption that every bit signifies a positive contribution to the value of the number. Signed representations make the assumption that the most significant bit is used to create positive and negative values, and they come in three flavors: sign and magnitude, 1's complement and 2's complement. We have learned this in digital design where the computer uses 2's complement to represent a negative number and for computation. Now, you will be introduced to the ARM's microprocessor instruction set. They are grouped as follows. Moving data within the processor, which means moving data from one register to another register. Memory access, where instruction is to move the data from the memory to the processor or from the processor to the memory. Arithmetic operations which are add, sub, multiply and divide. Logic operations such as AND, OR, NOT, and XOR. Shift, and rotate operations, where the data is shifted bit by bit, from left to right, or from right to left. And the last one is how to control the program flow. We will start with a simple move instruction, which is the instruction to move the data from a register to another register, the MOV instruction. The format is like this. This we call an opcode and this we call the operands. In this example, there are two operands. RM is the source operand, and RD is the destination operand. Given the instruction as MOV, R2, R0 means move data from register R0 to R2. And the size of the operation is 32-bit, or in word size. Let's the initial content of R0 is 1, 2, 3, 4, 5, 6, 7, 8, in hexadecimal format, and the initial content of R2 is 0. After the microprocessor executes the instruction, the content of R0 is copied, or in computer, it is called move, to register R2. Like this. This instruction is called move immediate. It is used to move the data from the programmer or from the outside into the CPU register, where the size of the source operand is 16-bit. For example, if the instruction is to move immediate 9 into R0. After the microprocessor executes the instruction, we will have 9 in R0. For the negative immediate value, for example -9, the value will be stored as 2's complement representation like this, and the sign bit is extended to bit 31. Just now we have learned that the size of the immediate value is 16-bit. But how to move a 32-bit value into a register? For example, we want to move ABCD 1 2 3 4 into R0, like this. The answer is to move 16-bit 2 times. One is for the lower half word and another one is for the higher half word, using move W and move T instructions, respectively. This is move W instruction where it's used to move immediate halfword value into the lower halfword of the register. This instruction will not affect the higher halfword of the register. For example, when we want to move a halfword data 1 2 3 4 hexadecimal into R0, the instruction is move WR0, followed by the immediate value 1 2 3 4. After the microprocessor execute the instruction, register R0 will have halfword 1 2 3 4. And this is move T, to move a halfword immediate value into the top halfword of a register. For example, if we initially have this value in R0. After we execute the instruction, register R0 will get the immediate value ABCD at the top halfword of the register, just like this. The last move instruction will be MVN, or the move not. This instruction will move the complement value of the immediate value. For example, when we move not immediate value 1 into R0, we will have 7 FE in R0. Note that this 7 FE is the 32-bit first complement of number 1. Now, before we go further to the load and store instructions, let's simulate the instructions that we have learned using Kyle Microvision. On your PC, launch the Kyle Microvision. Click the project, and choose New Microvision Project. Create a new project folder. For example, PR4 2020. Make sure that the name must always start with alphabet. Name the project as PR4 2020 as well. Now, for this Windows, select ARM. ARM Cortex-M3. And ARM CM3. Click OK. For this Windows, select CM-Sys. And tick Core. Then, select Device. Tick Startup. And click OK. Now, when we want to write our first assembly program. So, we need to create an assembly file by expanding the target 1. Then right-click the source group 1. Add new item to group. Select assembly file. With .s. Name the file as PR4_2020 as well. To write an assembly program in Kyle, we need to have the header file like this. Which are the assembler directives? Type area to define the area of the code in memory which is read-only part of the memory. Then type this following lines. This is a must, to define the starting line of the code. Now, let's try to write the code that we have learned from the previous slide, which is the move instruction. First, we move wide immediate hexadecimal 5, 6, 7, 8 into R0, followed by move top hexadecimal 1, 2, 3, 4 into R0. Then we move the content of R0 to R2 as follow. Finally, we put the endless loop here, followed by the end assembler directive to indicate that the program is ending here. Now, we can simulate and see what happened to the register when the microprocessor executes these instructions. To do that, we need to compile the codes by selecting Project, Build Target, or just click this button. Make sure that there is no error in the build output window. To simulate, we will use the Debug tool, by selecting Debug, then Start or Stop Debug Session. Or just click this button. But before that, we need to set the debug to the simulation mode by right-click the Target 1 and option for Target 1. Debug. Then tick Use Simulator. Make sure that all the settings are like this. After all the required setting are done, let's do the simulation. Press the Debug button. Click OK for this message as our version is the free version which limit to 32K of program size. Now, we can see all the registers are here in this window. To simulate our code, mark the cursor at the first line of the code. Then click Run to cursor line. Or press Ctrl F10. To execute the instruction, click the Step 1 line. Or press F11. When we press F11, the instruction will be executed, and we can see the lower halfword of R0 as now contains hexadecimal 5, 6, 7, 8. Then observe that the cursor will move to the next instruction to be executed. When we press Step 1 line, again, this MOVT instruction will be executed, resulting hexadecimal 1, 2, 3, 4 in top halfword of R0. When we execute the MOV, R2, R0, we can see that the content of R0 is now copied to R2. Now, let's continue with the next group of instructions, which are memory access instructions. The ARM processors use the load and store instruction to access memory instead of using the move instructions as in CISC processors. This means, data manipulation must be done in the registers. For example, to add the data in 2 or more memory locations, the data must be loaded into the register, then, perform the addition process, and store back into the memory. In this section, we will also examine the addressing modes that can be used in order to access the memory. Now, we will look at instructions for storing data from a register into a memory location, and reading data from memory location to a register. ARM processors use indirect addressing mode to store the data from the register to the memory, or load from memory to register, where the address of the memory location that we want to store or load the data must first be loaded into the register. This register will act as a pointer to the target memory location. The instruction format looks like this: STR for store, or LDR for load. For STR, RD is the source operand, while for LDR, RM now is the source operand. The square bracket indicates the direct addressing mode. Means that the content of the register is not data, but the address that we want to access. For example, if we want to store data from register R1 to memory location or address 20 million hex. First we need to have the address 20 million hex in R0. Then, the instruction will be strr1 for source operand, comma, and in square bracket R0. Therefore, R0 will point to the address 20 million hex in the memory. After we execute the instruction, the word data from R1 will be moved to the memory, like this. Observe that, the data will occupy 4 memory locations form address 20 million to 20 million 3 hex. The reason for this is that, one memory location is 1 byte. Given the data is word size, or 32-bit, therefore, we need 4 memory locations to store that data. The hexadecimal 20 million in R0 is called an effective address. Observe that the least significant byte, the hex 78, of the data is stored at the least significant address in the memory. This storing mode is called little endian mode. By default, ARM processors use the little endian modes. Some ARM processors support both little and big endian modes. This mode can be changed using special instruction. However, the supported memory type also depends on the design of the rest of the microcontroller, bus connections, memory controllers, peripherals, and so on. Now, we will look at storing halfword value from the register to the memory. R1 is now the source operand and R0 is the destination operand. R0 contains the effective address, which is the address that we want to move the content of R1 to. After we execute the instruction, the lower halfword of R1 will be copied to the memory address hex 20 million and 20 million 1. The first address will get hex 78, while the next address will get hex 56. Observe that, only 2 bytes are required to store halfword value. For the store byte, only byte value from R1 is copied to the address pointed by R0, which is hex 20 million. Now, we will look at load instruction. The LDR. Observe that, now the left-hand operand is the destination operand, while the right-hand operand is the source operand. This LDR instruction will move the 32-bit value or word size from the memory into the register. For example, for the instruction LDR R2R0, with the initial contents of R0, R1, and R2 are given here. This means the effective address is hex 20 million because the content of R0 is hex 20 million. Hence, we will move the 32-bit data from the memory address hex 20 million to 20 million 3 into register R2. The data is AA, BB, CC and DD. After the instruction is executed, the content of R2 is now updated to DD, CC, BB, and AA according to little endian mode. For the LDRH, or load halfword, when we execute the instruction, we will get the halfword value from the memory in the register. In this case, as the effective address is hex 20 million. Therefore, we will move the value AA and BB into the lower halfword of R2. And, as for load byte, we will move the byte value from the address hex 20 million into R2 like this. The next addressing mode will be the indirect addressing with offset. For this addressing mode, we will set the base address stored in the general purpose register. Then we can access the data in the memory by using the effective address generated by the base address and the offset. This kind of addressing mode is useful for manipulating data in the memory or implementing data structure. For example, data sorting and searching. The offset can be an immediate value or a value in a register. The size of the offset must be between -255 to 4095. The base address in RM combined with the offset value to form an effective address. For example, this store byte instruction will move the data from R1 to the memory address generated by the value in R0, which is hex 20 million, an offset value, which is an immediate value, 2. Therefore, the effective address is hex 20 million plus 2, resulting in effective address equal to hex 20 million 2. For this, the byte data from R1, which is hex 78, will be moved to memory address hex 20 million 2, as illustrated here. Another variant of the addressing mode with offset is the PostIndexed addressing mode. The format of this instruction is like this. The offset is the immediate value, outside the square bracket. The size of the offset must be between -255 to 255. The base address RM forms the effective address. The key observation here is, the base address is updated with the new value, which is the offset value after the instruction is executed. As shown in this example, the effective address is the value in R0, which is hex 20 million. The byte data from R1 is then moved into memory address hex 20 million. After that, the content of R0 is updated to a new value, which is hex 20 million 2. Besides the post-indexed, we also have the pre-indexed addressing mode. The format of the pre-indexed addressing mode is like this. The offset is now inside the square bracket with the base address. The exclamation mark here indicates the pre-indexed addressing. The key observation here is that the base address is updated with the new value before the instruction is executed. The base address in RM is combined with the offset value to form an effective address. This example illustrates how the pre-indexed addressing mode is executed in the microprocessor. First, the value in R0 is updated with the effective address, which is hex 20 million plus 2. Then the byte value from R1 is moved to address hex 20 million 2. We will do some simulation in Kyle to simulate the load store instructions with its addressing mode variants. Now, launch Kyle software. This is the code to demonstrate what we have learned in the previous slides. First, we need to move the base address into R0. Then, move the data into R1. Finally, execute the str instruction. Now we will try to simulate the code. Because we want to see the content of memory, therefore, we need to view the memory by selecting View, Memory Windows, and select one of the memory windows here. Then, we need to go to the address that we want to look at. In our case, address hex 20 million. Execute the program, line by line. We can see that the word data from R1 is now in the memory from address hex 20 million to 20,000,003. Observe the little Endian format here. The address of the memory is read like this. Here is address hex 20 million, the next is address 20,000,001, 2, 3, 4, and so on. For the other addressing modes, you can try to simulate on your own to help you understand more on this subject. The first part of the lecture for Chapter 3 will end here. We will continue the next part of the lecture in the next video. Hope you enjoy the class. Any questions regarding this lecture, you can send message to me using Edmodo, or just post on the Edmodo feed so that we can openly discuss. Thank you, and goodbye.